Now I love Carmenta. This is kind of like my favorite, because as you can see on the bottom right, it's already been acquired. So we went from public data, which people think is as valueless as kitten videos, to the acquisition in 24 months. Inventors happy, investors happy. Of course we're going to do more of these. I'm giving away the secrets here, because every one of you could take a different disease to make a diagnostic for, and we'd never step on each other's toes. That's how many diagnostics we need in medicine. Let's move on to another diagnostic, DNA sequencing. It's going to be a crazy time. There are still naysayers, but we're going to be using DNA. The Genome Project, the original Genome Project, took 13 years to complete. It cost $3 billion. It was done in factory-like settings like this. This is the Whitehead Institute in Cambridge, Massachusetts. Even this was a state-of-the-art. And now this is my hand holding a USB stick sequencer. This is Oxford Nanopore. It's a no-brainer. We're going to be using these in medicine. I got involved again while I was still at Stanford, because we had the first patient show up with a genome sequence. This is Steve Quake. He's a faculty member at Stanford. He starts companies on the side, sequencing companies. And he showed up because here's Steve, his nephew at age 19 over here, one morning died of sudden death, did not wake up one morning. And so Steve Quake went to his cardiologist and our good friend Ewan Ashley and said, well, doctor, am I going to die of sudden death? Here's my genome, doctor. Right? This was back in 2009. This is very early days. Of course, we studied all the heart genes to figure out if it has any lethal kind of, arrhythmia types of risk. He doesn't have any of those. But then my job was to figure out all the rest of medicine. Heart was all set. What about every other disease that he could possibly get in his lifetime? And that's when we got to the next big data, and that is the publications. Researchers lock up all these gene correlations in publications. And we realized there was no master database of just every spot in the DNA and every disease. So we started with a San Jose high school kid one summer, gave him 50 papers to read, and he started to curate all of them. We made a data model. Let's get every fact we can out of these papers. And if a San Jose high school kid can do this 50 papers in a summer, we just extrapolated how long would it take to read the entire literature in human disease genetics. And that's what we did. So here are 100 papers, here are 1,000 papers. I have a Perl script that makes these. And we blew through 20,000 papers. We essentially read them all. And we then were able to tell, for example, which diseases he's going to be at risk for in the future, and then all the environmental factors on the side that might make a difference, right? Because it's not going to be doctors giving you depressing news. You're going to die of this, this, or this. You'll never go back to that doctor, right? Instead, it's all about the controllable factors. Yeah, that'll be a real cheery type of physical example. It's all about the controllable factors, which I think is the prescription pad of the future, right? What do you change in your life? Well, Steve, exercise, diet, smoking, and alcohol. Well, probably don't need a genome for those four, I can tell you that. But tiny font up here is pesticides and Parkinson's disease. He's had slightly higher risk for Parkinson's, and 10 papers were written linking pesticides. I didn't write those papers, we just curated and made a graphic like this. Like that, we were able to tell cancer risk and things like that. What do you do next in Silicon Valley? You start a company on that. This became Personalis. Now Personalis has blown past, 150 employees. They're over right next to Facebook in Mountain View. And they've raised $76 million now past Series C. They're doing okay. They're in cancer sequencing now. If you're a patient at the VA hospital anywhere in the country and you need your cancer sequencing, actually comes to Menlo Park for Personalis. And also if you're part of the Million Veterans Program, all those genomes come to Personalis as well, using public big data. So that's what we did. We did a bunch of these. This one just came out last summer. I could show you dozens. This is one of the more later ones, just came out last summer. UCSF and Stanford collaboration. This is for a disease called liver cancer, hepatocellular carcinoma. 350,000 people a year get liver cancer. But for better or for worse, very few in the United States. And because of that, they don't make many drugs for this, right? It's an India-China problem, right? It's hepatitis, it's alcoholism. Not a lot of companies working on this. And so this drug, we computed, using public data, we computed nicotinamide should work. That's a worm drug. If you have a problem with worms in your GI tract, or your pet does, you take nicotinamide. And this is human cancer in a mouse. It's out of control. Nicotinamide is slightly better. NEN is nicotinamide ethylolamide. It's a particular salt. You can just take this by pill. You don't even need an injection. And you can see how much better that is. Glowing cancer is on the right here. Where is it? Yeah, so without the drug, with the drug, much better. And we actually do have one drug for liver cancer. It's old UCSF Onyx pharmaceutical drugs called sorafenib. And you can actually test no drug, nicotinamide, sorafenib. These two both work kinda. Together, they work even better than separately. That means it's synergistic. That means this new drug works in a new way. And so if we're going to launch clinical trials on this one, we do it with a combination here.